now. Okay, so first off, so we did fix that pre-screening issue where a student accidentally basically restricted our study from showing up in some of the 104 students' choices. That happened for about a week, which appeared to have slowed down the rate at which participants sign up for our group project one. And that has been resolved, and I've been monitoring closely the rate of signups over the weekend. They've picked up a little bit, but they are still definitely slower than they were last year. And it seems quite clear to me now that the rate of signups is simply going to be slower this semester than it was last year. And it has something to do, I'm still trying to figure it out, and I've talked to the chair several times, something to do with the fact that all studies are online. My theory is that students were required to take a certain amount of in-person studies last year, which all of these studies last year would have been in person. And there was less in-person studies to sign up for, and there was a few studies, not very many in-person studies going on last year. And so participants had to sign up for the group projects in this class last year. Now, all studies are online, including ours. And so we're one of like 20 studies. And so students are signing up at the same rate in general as they did last year, but now we are one of many online studies instead of being one of the few in-person studies. So that's my theory. The way we're going to address this, one, I'm going to see if things pick up. We waited over the weekend, and I counted there's since Friday, there's been 6 people sign up, which is still way slower than last year. So we're going to see if that picks up during the week. But what I'm going to do right now is I'm going to tell you, or I'm going to suggest that you run 2 friends or family members on your study now. So this is a new thing. This should make it easier. Originally, I wanted you to run 8 participants all in SONA system. I still want you to run 8 total participants for your group, but now 2 of them can be friends or family. Let's see, and I want you to use the group project like the group sign up sheet, or the group sheet that I had the Google sheet for previously, which says each of your group numbers, and it has the participant ID numbers for each of your groups. That's something that I linked out 2 or 3 weeks ago. I see a chat. Let me check this out real quick. Yeah, so 2 out of the 8. Ahmed asked, do you need 2 per person? No, you just need, out of your entire group, you can have now, this is allowance. You can, instead of running 8 people all from SONA for your group, you can run 2 people can be friends and family that you can just email the link to. So this is, the purpose of this is to make it so you don't have to collect all of your data on SONA, which will save us a little bit of time. You can email friends or family. My request for this, though, is that you email people the link that I think like don't already know the purpose of the study. So if you've told your roommate the purpose of our study, please don't let them be the person that does it, because I don't want the results to be tainted. Anyway, back to how you're going to do this. There is that Google sheet that I provided to you 2 or 3 weeks ago that has all of your group numbers on it. It also has different columns for which participant IDs go with each group. I've entered a 3rd column now. And the way I want you to, so go check out that Google sheet. But in this 3rd column, basically what you'll be doing is, if you are group 1, your participants were your participant IDs were 1 through 8. If you had extra credit participants, you might remember you can do extra credit participants, then that was the extra credit participant IDs were 101 through 108. And now if you run family and friends, I want you to have them use the following participant ID, FF, and then if you were group 1, then it would be like 201. So it was just 1 through 8 for regular participants for group 1, and then the extra credit participants was like 101 through 108. And if it's family and friends, I want you to have the FF prefix in front, and then use 200s for these people. And it's important that I'm only going to allow you to have, right now, I might change this later. I'm only going to allow you to have 2 friends and family for now, but I might change that later if things don't pick up. Okay, let me see this chat right here. That's a good question. Danny asked, for extra credit participants, can you use friends and family members? I'm going to say no for now, but I might change that later. I'm going to say no for now, but I think I probably will change it later. But I'll give an announcement regarding that Wednesday. Right now, I'm only going to allow 2 friends and family, but I will change that. I might change that later, and we could revisit this issue regarding including more friends and family later for extra credit. Okay, so that's that. So another thing that I'm changing here, I'm adding a simple assignment. Oh, another question or comment. Good, I'm glad you're asking. Let's see what this one says. Participant ID, Abigail's asking, can I explain the participant ID one more time? Sorry, let me see if I can find some of this stuff. Okay, here is the participant ID. Like, these are your different group numbers right here. And we did talk about this previously. So when you're signing up your participants for your study, you have to send them 3 things. We talked about this previously. And one of those 3 things is a participant ID number. They type this participant ID number into Psy Toolkit. At the very beginning, the very first survey question they get is please enter your participant ID. And group number 1 right here, these people, their participant IDs are 1 through 8. And so your first 8 participants in this group should just have, I should expect there to be 8 data files. And one of them will be with participant 1, another participant 2 through 8. If you have extra credit participants, you're going to email those people these participant IDs right here. That is 101 through 108. And then people that are friends and family, though. So these people right here are SONA system only. These people would be extra credit through SONA system only. And then right here, the FF column, these are people that are friends and family. So these people will be in the 200s, and if you want to have them, and then you can have them put an FF in front, though you don't really have to have the FF. If you just have them put a number in the 200s, I will know that they are friends and family, but it wouldn't hurt if they put the FF too. That's your call. Does that answer your question, Abby? Yes, good. Okay, good. So anything else, people, regarding this? Okay, so I am adding an additional assignment because we've had this delay. Some of the things that we would have been doing, I want to do this now so that we're going to do something now instead of doing it later. And I've added it'll be a very simple assignment, I believe, for you, but it's one that we need to get something on group project 1 regarding data analysis started because we're a little bit behind on that now. So I'm going to group project 1. So I've added this right here at the very bottom, group project 1 first data file. So some of the groups haven't run a participant yet, but luckily some have, and I saw that there were 5 or 6 people that have signed up since Thursday afternoon. So a lot of groups are getting the first participant. So I want you, this will be easy points, I think, but it's just to get us moving a little bit on making sure that we're on the right track. We're writing data compilation and analysis for group project 1. I want you to take your first data file and then import it into Microsoft Excel like we've been doing for all of the labs. And I want you to compile the data for group project 1 into the 4 conditions, which are shown here: Mozart congruent, Mozart incongruent, range times congruent, range times incongruent. And then you compile them, make sure that the dependent variable is correct reaction time. So it's not just reaction times, it's reaction times only on correct trials. And then make sure that you calculate the correct means for each of the 4 conditions. You just need to do that for 1 participant. And then you're going to, into Yeah, and then you'll turn in the Excel sheet. So import one data file into Excel. Your first participant that you run can either be friend or family member, or it can be a person from Sona if you've already done Sona participants. Import that into Excel, compile everything like we've been doing, and there's some instructions here on Blackboard, and then that's going to be due, I think I made this due Friday. Yeah, it's due Friday. So this is just to make sure that, you know, getting something, whatever we can do right now regarding data compilation for this study. We just need to get something done because we're a little bit behind otherwise in data collection. Any questions about this assignment? It should be pretty straightforward, and it's basically what we've been doing for part ones of all of our labs so far. Any questions or comments about that? All right. So for the remainder of the time, we will just talk about the stuff that is planned for today on the syllabus. Hemispheric differences, which was the topic of our lab that we did Friday. We had these two articles. Originally, they were due today, but I moved the due dates back for these quizzes. I think I made these quizzes due Friday as well. So there's going to be several things due Friday. So we'll talk about all this stuff today, and it's all related. The general topic for this whole class is basically hemispheric differences, and I guess I'll situate this in terms of, out of all of the method, you know, the main method that we've been using so far in this class is reaction time, which is kind of on the border of being considered a physiological method. There's not external sensors placed on your skin when we're measuring reaction time. But reaction time does have high temporal precision, which is a characteristic of many physiological measures. And I'm reminding, this is something we talked about at the beginning of the semester. One of the reasons we're focusing on reaction time is because it has high temporal precision, just like many of the physiological measures that we're not able to use because we're having to, you know, social distance. We're having mostly online. Everything's online for this class. But the Hemifield method and the dichotic method, these are actually would be considered another type of physiological measure. And the reason why these are considered physiological measures is because they are quite directly measuring brain function. It's a completely behavioral task. The Hemifield and dichotic methods are completely behavioral, but they're published in neuroscience journals. And so it's a purely behavioral method, but it really is getting at something quite physiological. So this is another method that is really in a class where we're forced to do everything behavioral. It makes sense in a physiological class because it's definitely investigates, or it appears to be investigating brain function. So here's basically how these two paradigms work, Hemifield and dichotic listening paradigms. In the Hemifield paradigm, this is visual. This is the idea that information was presented to the left side of your world, that is the left hemifield, projects primarily to your right hemisphere of your brain, and information which is presented to the right side of the world, that is the right hemifield, is projected primarily to the left hemisphere of your brain. And so you can look and investigate using this idea. You can investigate differences in the functions of the left and right hemispheres of the brain. So that's like the visual version. When I say hemifield, I'm implying projecting things to the left or right sides of the visual world, and then that information goes to the contralateral brain hemisphere, contralateral meaning opposite. There's an analogous method, an analogous paradigm for the auditory modality, and that's the dichotic paradigm right here. So this refers to the hemifield paradigm. The dichotic paradigm assumes that information presented to each ear goes to the contralateral hemisphere. So information presented to your right ear is processed primarily by the left hemisphere, and information presented to your left ear is processed primarily in the right hemisphere of your brain. So this, I think I have a picture here. Yeah, this is taken from a cognitive neuroscience textbook. This is a pretty common diagram which illustrates the way things work regarding hemifields. That is, in the visual modality, information in the left hemifield goes to the right hemisphere, information from the right hemifield goes to the left hemisphere of the brain. You can see that here. So in this diagram, the left visual field is over here to the red, and you can see information on the left side of the world that goes to the left eye, and it contacts the left eye over here on the right side of the eye. And it also contacts the right eye on the right side of the eye. So you can see information from the left visual field is landing on two different eyes, but it lands on both sides of the eyes on the right side of each eye. And that information from the left visual field, if you follow the red line, ends up primarily in the right hemisphere of the brain. You can see that right here. The red ends up primarily in the right hemisphere of the brain. And similarly, information in the right visual field hits the left side of the left eye and it hits the left side of the right eye. And that information travels to primarily to the left hemisphere of the brain. So one thing I want to emphasize is it's not that the left, in the auditory modality, the right ear goes to the left hemisphere, the left ear goes to the right hemisphere. It's a little different for vision. It's not that the right eye goes to the left hemisphere and the left eye goes to the right hemisphere. It's not each eye, it's the visual field. The left visual field, which projects to both eyes, ends up in the right hemisphere. The right visual field, which also projects to both eyes, that information ends up in the left hemisphere. So in the auditory modality, each ear projects to the contralateral hemisphere, but in the visual modality, it's each visual field. It's not each eye that projects to the opposite hemisphere. It's each hemifield projects to the opposite hemisphere or the contralateral hemisphere. And so the reason why these paradigms are useful, and this is getting to what we did for lab number 6, is that they can be used to study hemispheric asymmetry or hemispheric differences in different types of perceptual and cognitive tasks. Probably the most popular studied would be hemispheric differences in speech tasks, which I imagine most of you have probably heard of the idea that speech perception or language perception is something which involves the left hemisphere more than the right hemisphere. I know there's some skepticism about this idea, at least that I read about in social media and stuff like that, but really the evidence is quite compelling that speech, for the most part, while there's a couple exceptions, a couple aspects of speech rely on the right hemisphere of the brain, most aspects of speech and language perception rely on the left hemisphere of the brain. This is a screenshot from a study that was published in PNAS, which is a highly ranked journal, high impact factor journal. And this was published like a month ago, right at the beginning of September. So this is really, really a hot off the presses study. It was an fMRI study looking at hemispheric differences in speech. The main thrust of this article was actually comparing people of different ages, young children, middle children, older children, and then adults, comparing their brain function, their brain's responses to language. I'm not going to talk in detail about the developmental changes. That's something they do talk about in the article. Really, I just want to understand the overall pattern of hemispheric differences that were shown in this study. Participants in the study listened to speech that was either forward, so obviously forward speech is just normal speech, and then backward speech is if you take the exact same things but you flip the sound wave, and it usually sounds like that, completely weird. It's hard to do an impersonation of backward speech, but the purpose of backward speech is it's completely intelligible, or not intelligible. You cannot make it out at all. Backward speech, you can't parse it at all. It makes no sense when you hear backward speech. Forward speech is normal speech. Backward speech, it sounds like you just can't make out anything at all. And so they presented forward and backward speech to the participants in this study while fMRI was recording their brain activity, and they wanted to compare what is the differences in brain activity between forward speech, which you can comprehend, which you can make sense out of, versus backward speech, which is basically sounds which you cannot make any sense out of. And then they compare bold response, which basically means it's metabolic activity or blood flow in the brain between these two conditions. And shown on top is the left hemisphere of the brain, and then shown on the bottom is the right hemisphere of the brain. And these are shown here, and it kind of says down here, these are basically regions of the brain that were more active in the comprehensible, that is the forward speech condition compared to the backward, the incomprehensible speech condition. These were regions of the brain that were more activated when people could understand what the words were saying that they were hearing. And you can see that there's lots of activation in the left hemisphere. There's some activation in the right hemisphere, but there's clearly much more activation in the left hemisphere. So really, this is kind of uncontroversial to brain scientists. It's quite clear that when you're listening and understanding speech, the left hemisphere of the brain tends to be more involved than the right. The right's still doing something, but the left is doing more things than the right. And this fMRI study is one of several, but this one's really new, and it's really new, and the effects are really strong. Left hemisphere is pretty clearly dominant for speech comprehension, language comprehension. Here's another one. I'm showing you this one though because they're looking at isolated words. This is an older one, an older study, but it's kind of getting at the same idea, except instead of doing entire sentences like they did in the previous one, this one is just doing individual words, and also people are reading the words in this study rather than hearing the words like they were in the previous one. And so the factor is composed of these two levels right here. So like coherent words like this appears to be the word dynamite. It's taking those different line segments and arranging them so that they form the word dynamite, which is a word, obviously. And then you can take those same line segments and scramble them so that they don't say anything. You're still seeing the same line segments, but they're no longer forming a coherent word. And you're comparing brain activation with fMRI between these two conditions. We got a question here. That's not related to the lecture. I'll answer that later. Okay, so you're comparing the activation for these two conditions right here. And right here, this is the left hemisphere. Right here, this is the right hemisphere. And you can see that there's more activation in response to the word dynamite in the left hemisphere than there is the scrambled line segments right here. So this is getting at the same idea. When these are regions of the brain, once again, more active for this condition than that. There's still some activation in the right hemisphere, but the majority of the activation in this study was in the left hemisphere, getting to this idea that speech perception, even though in this case it's written speech, it's reading, involves the left hemisphere more than it does the right hemisphere. Here's another study. Now this one involves face perception. It's another fMRI study, but it's kind of an analogous paradigm as the other two that we just saw for words and language. This one is kind of a similar thing for faces. One condition, people would see an intact face. In another condition, they would see this, they would take the pixels that comprise this picture, but they would just randomly place those, they would randomly scramble or shuffle all of the pixels that compose this picture. They would randomly scramble them until they look like this. So obviously it's basically a face compared to a noise, basically a nothing picture. And they're comparing the brain activation between the two conditions with fMRI. And what they generally find for face studies, this is the right hemisphere, right hemisphere, right hemisphere. They tend to find more, there's activation in both hemispheres, but for face studies, there tends to be more activation in the right hemisphere compared to the left when you're looking at a face compared to some other type of object. So fMRI studies, pretty darn clear. The left hemisphere tends to be more activated when people are doing a speech language task, whether it's listening to an entire sentence or whether it's listening to a single word or reading a single word. Left hemisphere is more important for speech. The right hemisphere tends to be more important for face perception. You can see here, this red blob in particular, really strong in the right hemisphere. In general, there's a little bit more activation in the right hemisphere than the left for faces. So this brings to Hemifield 1. So even when this course was normal and we were meeting in person and doing labs, we're never doing fMRI studies because one thing, fMRI studies, cost thousands of dollars per participant. So we obviously don't have that kind of money for this class. But the same types of findings that you can get from fMRI studies, you can actually study these with purely behavioral measures like the Hemifield paradigm, which is the topic of Hemifield 1, which is one of the studies. Originally it was due today, but I extended the deadline because of some of the chaos related to participants recently. So this is due, articles due Friday. Usually you've read them before I've talked about them. So these quizzes should be extra easy for you this time because I will have already talked about them and you will have read them when you take the quizzes eventually. But these studies, the findings from the study converge very nicely with the studies of the fMRI studies that I just showed. In Hemifield 1, participants were shown on each trial either 2 faces or they were shown 2 words. The first face or first word was presented in the center of screen. It was presented for a relatively long amount of time, 750 milliseconds, which is 3/4 of 1 second. More than enough time to be able to read the word or to process, what the image of the face looks like. That's the first word or first face on each trial that you would see. Then you would see a second, if the first thing you saw was a face, then you would see another face. But that second face that you saw would be presented either in the left visual field or the right visual field, and it would occur very quickly. So here, the second face presented for only 150 milliseconds. So this is less than 1/5 of 1 second. And then your task is to determine, you either saw 2 faces on a trial or you saw 2 words on a given trial. And your task is to indicate were the 2 faces or the 2 words that you saw the same or different. And it's a little bit of a hard task in particular because that second word appears for only 150 milliseconds. And it does so either in your left or your right visual fields. That is the left peripheral vision or your right peripheral vision. And so the dependent variable for this study is their accuracy. How accurate were people at performing this task? Are the 2 stimuli the same or different? Depending on whether that second stimulus was presented in the left visual field or the right visual field. And they did show a really strong stimulus type by Hemifield interaction. I think I got the figure, right here. So there's more figures than this in the article, and I do ask you about some of those other figures on the quiz, though for our purposes today, this is probably the most important figure, which is the study from the adults. This shows that significant 2-way interaction. And we've actually had lots of examples of 2-way interactions in this class now. So hopefully you can kind of see the interaction, but just in case, I will kind of spell it out.
Before you do that, can I ask a quick question?
Please, yeah.
Sorry to interrupt. So were they shown, so like if I was a participant, would I see a face for 750 milliseconds and then another face for 150?
Yes.
Okay, so it was the same.
Yes.
Okay, gotcha. That was
you would always see the same 2 things. You would never see a face and then a word on the same
Okay.
time. It was always a face and then another face, or a word and then another word. Thank you for that clarification question.
Yeah, thanks.
And so here's the 2-way interaction. The 2 factors, the 2 independent variables. The first one, this is type of stimulus composed of faces and words. And then the second factor, the second independent variable is hemifield, left visual field, right visual field. And they found the interaction between these 2 factors. And you can see that here. So my strategy, the way I always look at interactions when I'm looking at graphs, there's several different strategies. I talked about both of them previously. But the one that I always used when I'm reading papers, and I read lots of papers, is I look at each cluster of bars and I kind of assess the overall pattern. And I would say here for faces, there's a downward pattern. And that means that for faces, they're more accurate in the left visual field than they are the right visual field. And you can kind of see it's like a downward pattern there. And they're more accurate for faces in the left visual field, which suggests, by the way, that faces are preferentially processed in the right hemisphere of the brain. Looking at the words, on the other hand, it's like an increasing pattern. This one over here is going down, but for the words, it's going up. And if you describe that more closely, basically, I would say something along the lines of words are more accurately processed when they're presented in the right visual field compared to the left visual field. So once again, when I'm looking at for interactions on graph, I always look at each cluster of bars and compare the pattern. And here, this is a downward pattern. Here, this is an upward pattern. So that's a strong interaction because the 2 patterns are different. In other faces are better accuracy in the left visual field. words are better accuracy in the right visual field. So that's a pretty textbook looking interaction right there, actually. And it suggests words are more strongly processed in the left hemisphere of the brain, where faces are more strongly processed in the right hemisphere of the brain. And really, there are hundreds of studies which show this, especially for words. These studies are lots and lots and lots and lots and lots and lots of studies that show the same thing for words. There's a decent amount for faces, but at least as far as I can see, there's more available evidence supporting this idea for words than there are for faces, though there's definitely lots of evidence for both. Here is dichotic 1 study. This is getting at the same thing, but this is a speech study. So dichotic is presenting syllables, presented two syllables presented on each trial simultaneously. One syllable to the left ear, one syllable to the right ear. And so some examples on a given trial, you, the participant, might hear the syllable ba in your left ear and the syllable ga in your right ear. Or on a different trial, you might hear in your left ear ah and in your right ear eh. And so the difference between these, I included these to illustrate that there are different types of trials in dichotic 1. Some of the trials, the crucial difference between the things in each ear is a consonant, ba versus ga, b versus g. The difference is a consonant. But for some other trials, the thing that differed between the two ears were vowels, so A versus E. Here, the difference is just the vowel sound. Here, the difference is the consonant sound. So whether participants were presented with 2 different consonant sounds, like these trials, or 2 different vowel sounds, like trials like these, the participants performed the same task, and their task was report all of the speech sounds that you can hear. There was 2 speech sounds. The authors, if you look closely, they basically said participants were able to usually hear 1 speech sound, but the other one they usually were always wrong about. And so they didn't even process. They would usually just take the participant's first response was right a good amount of the time, but the second response was almost always wrong. Nevertheless, participants were asked to try and report the speech sounds that were presented in both ears. I think I got the data for those, yeah. So here are the data. By the way, this study is really old. It's from the 60s, but it's classic. It's been cited many, many, many times. And the findings kind of support this idea that the left hemisphere is more important for speech perception, though it qualifies, it puts an interesting spin on the idea that the left hemisphere is more important for speech perception. So the evidence in support of the idea that the left hemisphere is important for speech perception comes when you're looking at the consonants. So the dependent variable here is mean percent correct for their first preferences. So the first word that they say that they heard, you're supposed to say, what are the 2 words you heard in your ear? And they were almost always wrong with the second guess. But the first preference, the first guess, they were right, a decent amount of time. These are basically the percentage of time that they correctly got the word that was presented in their left ear compared to the percentage of time that they got the word presented correctly reported the word presented to their right ear. And you can see that 45% of the words presented to the right ear they got right, whereas they only got 31% of the words presented to their left ear. This is for the consonants. So ba versus ga, that type of comparison. Ba presented to the left ear, ga presented to the right ear. They would hear, ga 45% of the time, but they would only hear that ba in the left ear 31% of the time. So this supports this idea of left hemisphere dominance for speech perception because they were more accurate in the right ear. And the idea is that the right ear projects primarily to the left hemisphere and the left ear projects primarily to the right hemisphere. So this right ear advantage for comparing consonants between the 2 ears suggests that left hemisphere dominance for this type of speech sound. And you can see, by the way, this is a p-value right here. And this comparison using a t-test was significant. So, because this p-value is less than 0.05. And then for the vowels, this is kind of the surprising finding. For the vowels, they find that there is not a significant difference between the right and left ear. So you hear ah in the left ear and eh in the right ear. and then you have to report those speech sounds. 45% of the time, they would get the sound presented to their right ear correct, and 41% of the time, they would get sounds presented to their left ear correct. And so the trend is kind of there, where the right ear is a little bit higher than the left ear. But when they performed the statistical analysis, this was not a significant difference. So they found a strong significant difference for the consonant contrasts, suggesting left hemisphere dominance. But when they were doing vowels, there was not a significant difference. So the findings from this study, which are kind of interesting because many studies do show that the left hemisphere is more important for speech perception, but it actually turns out, and this has been replicated since this original study in the 60s, that appears that consonants in particular, which compose basically all words in the English language, consonants appear to actually be preferentially processed in the left hemisphere, whereas vowels are actually kind of equally weighted between the two hemispheres. So it's an interesting spin on the usual, the left hemisphere is more important for language and speech. That's true, but really if you look closely, it's more important for words that contain consonants. And if it's just vowels by themselves, then both hemispheres appear to be equally important. One thing that I want to point out that was problematic about this statistic, so this was back in the 60s, and this was like back in the 60s when ANOVA was discovered. And so this was before people were using ANOVAs frequently, because it was like a new discovery at that time, ANOVA, like 50 years ago, or 40 or 50 years ago. But they did not use an ANOVA. They should have done, I think I say it right here. They should have done a two-way ANOVA where the two factors would have been ear, left versus right, and type of stimulus, vowels versus consonants. That would have been a 2x2 ANOVA. But they didn't do that. Instead of doing the ANOVA, they did two separate t-tests, which if you remember back to statistics, that's considered a no to do two separate t. If you have two different factors, you're supposed to do an ANOVA instead of two different t-tests, because when you do two different t-tests, this increases the likelihood of false positives. As I said, this has been replicated. So despite the fact that they had kind of a shady statistical analysis, it's since been replicated in more modern researchers using correct statistical analyses, and they still find the correct, the same finding. Vowels are more bilaterally processed, whereas consonants are processed more in the left hemisphere of the brain. Okay, so let's see what we're doing on time. Yeah, not bad. Okay, so this is now getting really close to our lab 6, which is what we just did Friday. Basically what we did for lab 6 was the Riker-Wheeler paradigm, which is a famous study. This was also originally published in the 60s and happens to be, this is the first time I've ever done this, but it's one of my favorite studies. I was obsessed with it in graduate school. And I've liked it ever since. I've just never taken the time to have programmed it and collected data on it, but I did do that for this class. And I mean, I don't know if I showed it, but I was actually really excited about running this on you guys. I was trying to conceal it, I guess, a little bit, but I was really excited because I really like this study. And honestly, the data worked out perfectly. I was so excited over the weekend when I was looking at how perfectly the data turned out. And I'll show you those in a second. So the Riker-Wheeler paradigm, originally published in the late 60s, early 70s, it demonstrates what's now known as the word superiority effect. If you have taken Cog Psych here at KU, I believe all of the teachers that teach that will talk a little bit about the word superiority effect. And what the way this works and what the word superiority effect is, on each trial, you're shown a target stimulus, just like what we did in Lab 6. That target stimulus is either an entire word or it's just a single letter. And that target stimulus is presented briefly, if you guys are curious. The target stimuli that you saw in the Riker-Wheeler study that we did Friday, those stimuli were presented for 50 milliseconds, so 1/20th of a second. Very brief amount of time. The word is presented, or a single letter is presented for only 50 milliseconds. Then, just like what you guys did, the participants are shown two letters, and then one is above and one is below where that target stimulus appeared. The target stimulus, once again, is either a word or a single letter. And then the participants are shown two letters. They're basically like two options, or like two multiple choice options. One of those letters that appeared was in the target stimulus, and then the other letter was not. in the target stimulus. And your job as the participant is to indicate which of those two letters appeared at that position in the target stimulus. And the thing that's really, really surprising about the Riker-Wheeler paradigm is that participants, when the target stimulus is an entire word, they're more accurate at that task at choosing the correct letter. You know, they have these two letters. They have to choose which of those letters occurred at that position in the target stimulus. When the target stimulus is a word, they are better at this task than when the target stimulus is a single letter, which is, at least it's pretty surprising. I mean, most people that I talk to at least agree that the thing which is surprising about this is that words are composed of letters, many letters. And you would think that it would take more time to process a 4-letter word. It would be harder to process a 4-letter word than it would take to process a single letter, because a 4-letter word is just a word composed of 4 letters compared to a single letter, which is just 1 letter. So you would think people would be faster to process and more efficient to process a single letter rather than processing 4 letters, which happen to combine to form a word. But that's not the case. People generally are more accurate when the target stimulus is a word. The accuracy is higher than when the target stimulus is a single letter. And that's what we did find for our Riker-Wheeler study. So I add an additional variable. Usually for the Riker-Wheeler study, there's one factor, and that factor is type of target stimulus, whether the target stimulus is a word or a single letter. In the Riker-Wheeler effect, you usually could just use a t-test, and the t-test usually shows that accuracy is higher when the target stimulus is a word compared to when the target stimulus is a single letter. So for this lab 6, I wanted to replicate the Riker-Wheeler paradigm, but I added a variable, which was hemifield, which is one of the things that we've been talking about so far today in today's class, and what you'll be reading about for the articles, which are due Friday. So we did the Riker-Wheeler paradigm, but I combined it with the hemifield method. So one factor was type of stimulus, or the type of target stimulus, either a word or a single letter. The other factor was hemifield, whether the thing was presented in the left visual field or whether the thing was presented in the right visual field. So it's 2 factors. They're both within subject. It's a 2x2 repeated measures design. So let me show you the data right here. So this is the Google Sheet. We had 27 participants as of right now. This is the Google Sheet, the live Google Sheet right here. 27 participants. And I went ahead and these are the average amount that each person got correct for each of our 4 conditions right here. Those are the average amount. And those are perfectly acceptable numbers, but I figured it might make more sense if I converted those to percentages, because that's like, I don't know, something that we've had more practice with, more experience with dealing with percentages. So I simply converted them to percentages. So, and that's what's right here. So this is the average percent accuracy for each of these 4 conditions. So this is the average percent accuracy when the target stimulus is a word presented in the left visual field. And this is the target stimulus is a single letter presented in the left visual field. And if you look, almost 80% is definitely higher than 67.5 or 68%. So there's like an 11% difference right there, which shows the word superiority effect holds in the left hemifield. But the really interesting stuff is what's going on over here in the right visual field. Remember, this is a speech task, a word task. So we expect performance to be better in the right visual field. And that was the case, kind of, although it's definitely in the right direction, though we don't have a big enough sample size where it was significant yet. But it looks to me like if we had a bigger sample size, I'll show you the output in a second. In the right visual field, right here, these are words presented in the right visual field, 90% accuracy. And then a single letter presented in the right visual field was 65%. So in the right visual field, the difference between these two was, what is that? What's 90% minus 65%? 25% difference? Is that what that is? 25% difference in the right visual field between words and single letters. In the left visual field, the difference was around 11%. And so this is pretty interesting. So I'll go to the output now. Here are this is output taken from SPSS. Here are the descriptive statistics. So these are the means of the 4 conditions, though these are not converted to percentages. I used Excel or Google Sheet to convert things to percentages, but SPSS doesn't do that. So these are just the average amount correct for each of the 4 conditions. And you basically see the same type of thing. And words in the right visual field were more accurate than letters presented in the right visual field. Words presented in the left visual field were more accurate than letters presented in the left visual field. And so here are so for getting to the lab 6, part 2 that you will be doing, which is due Friday, you will be having to perform this exact analysis right here. I'm not going to show you how to do it this time because I've shown you how to do this exact analysis before. And if you want to have something that will help you remember how to perform this, lab 4, which was when we did the implicit association test for race, that was a 2-way repeated measures. That was a 2-way design. And so we did a very similar type of ANOVA for that one. This is a 2-way design as well. You will be doing a 2-way repeated measures ANOVA in SPSS, and you will need to get this output. So as you see, we have 27 participants. So when I'm looking at your output, I'll expect you to have at least 27 participants. It's possible that people will add data to the Google Sheet before then. So you might have more than 27, you might have 28 or 29 participants. That's fine. I'm looking for at least 27 participants. And you will report 3 F values. And if you look at what we did for the IAT one, lab 4, I actually showed you the 3 F values that were reported from that analysis. Let's see if I have, yeah, here's the lab 6 instructions more specifically. So for the lab analysis from lab 4, it was a 2-way design. You ran the 2-way ANOVA, and there were 3 F values that I reported. And I showed you all 3 of the F values in proper APA format. I showed you that way back in the lab 4 slides. That Monday, I showed you the output, and I showed you how to report the F values in correct APA formatting. So you should take a look at those APA formatted F values, because you can use the exact same format here. There's going to be a main effect of hemifield, and there's a main effect of stimulus type, and then there'll also be the hemifield by stimulus type interaction. The only one of these which is going to be significant is the main effect of stimulus type, and this is the word superiority effect. There will be and I'll show you right here on the output. Right here, these p-values are really, really small. They're less than 0.000. And this is the main effect of stimulus type. And what this is showing is that people did way more accurately when words were the target stimulus compared to when letters were the target stimulus. That's what the main effect of stimulus type. Words was the target stimulus were more accurate than an individual letter as the target stimulus. There was no main effect of hemifield, as shown right here. So overall, people were not more accurate in the right hemisphere than in the right hemifield compared to the left hemifield. However, this interaction is, I would call this marginal. It's not at the 0.05 level, but it's getting pretty close. And I strongly believe that if we doubled the sample size, this would be definitely a significant effect. And I want us to think about if this were significant, what that would mean. This is really important to understanding what interactions are and what they convey, the type of information they convey. This is almost significant. And I strongly believe that if we doubled sample size, it would become significant. And I want to understand what that would mean, what would that mean if it were significant. And so I'll have to show you this one more time. Once again, here's the interaction is basically comparing the difference between these two things compared to the difference between these two things. The difference between these two things, I'll actually calculate it, equals this minus this equals 25. And then I'll also compare these two things, equals this minus this equals 12. The difference in performance between words and single letters in the right visual field is 25%. That's a pretty big difference. In the left visual field, there's still a significant difference between words and single letters, but the difference is only 12%. So really the question is, the question of most theoretical importance in this study is the word superiority effect equally strong in the right visual field as it is in the left visual field? And that's what the interaction tells us. It tells us, is the strength of the word superiority effect, are they same or different in the right visual field and left visual field? 25% of a difference in the right visual field, 12% of a difference in the left visual field. That's a pretty darn big difference. Our sample size is small, so the interaction did not reach significance with the sample size of only 27, but those percentages are big. And I strongly hypothesize that if we increase the sample size, we would find that effect was significant. So this is Lab 6 Part 2. This is what I want you to work on for the rest of today. And there was a student that asked me a question about something unrelated to the lecture in the middle of lecture. If that student wants to stick around and ask me, that's fine. I also believe I have an appointment with another student. That student should stick around as well. But I am going to stop recording now.